so thank you to the organizers for inviting me to speak here. So I want to talk to you today about a certain... So I'll let those handouts get around a little bit. So I want to tell you about a fairly general approach for positivity problems. Okay, so we've seen that positivity problems are sort of an important part of geometric complexity theory. And what I mean by positivity problem is that we have some structure coefficient arising in geometry or representation theory that's known to be non-negative through the geometry or representation theory, like Kronecker coefficients or Plethism coefficients, or for instance, the multiplicity of an irreducible representation in the coordinate ring of the orbit closure of the determinant. So these are some coefficients we're interested in better understanding. And we want some efficient way of computing these non-negative coefficients. So from the complexity theoretic perspective, what the natural question to ask is for a sharp P formula for these coefficients. From the algebraic combinatorics perspective, we sort of want maybe a little bit more than that. So we also want some nice combinatorial object that counts this coefficient, like a Tableau with a certain satisfying some special conditions. And then we probably also want that formula to be sharp P. But the notion in algebraic combinatorics is not a precise one. Okay. I think sort of a lot of algebraic combinatorics is actually built around studying these positivity questions. Schubert intersection coefficients, QT-Koska polynomials, or something that's related to what I'll talk about today. So I want to just give you a brief overview of what I know about solving these problems. Okay, so the way I think of this is there's sort of a spectrum of approaches. On the one side, we can there are basis theoretic methods. Okay, and the other side, I'll write Tableau combinatorics. Okay, and so I think of these here as these are sort of more structured, or these are less structured. Okay, so basis theoretic methods, what I mean is maybe we have some, say, module for the symmetric group, and we want to decompose it into irreducibles. We want the multiplicity of some irreducible representation in that. Well, instead of just trying to get some combinatorial formula for those coefficients, we could ask for something stronger, which is for a basis for this module, such that subsets of this basis actually decompose it into irreducibles. Okay, so a subset of this basis actually spans an irreducible submodule. And from the labels of this basis, you can read off a combinatorial formula. This is almost the best solution you could hope for. And sometimes you can do this. So there are techniques using what's called canonical bases, or Kazan-Lustig bases, where you can produce very nice bases. Sometimes there are sort of less fancy methods using monomial bases or something like this. Okay, so maybe on the other side of the spectrum, there's just sort of playing around with Tableau combinatorics and words. And what I want to talk to you about today fits sort of in the middle here, is the theory of non-commutative Schur functions of Sergei Fomin and Curtis Green. And so there's a funny thing here, which is that so over on this side, when you're sort of demanding more for your solution to these problems, you would, I mean, it's more, so it's in some sense it's harder to do, but at the same time it could be easier, because what can happen is if you sort of specify exactly the right amount of structure you want to put on this solution, then maybe it will be unique, and then it's easier to find. Okay, so that's one of the games that you play here, is that there's sort of too many weird things you can do with Tableau to try to give you a combinatorial formula. But if you maybe demand more out of your solution, out of your combinatorial formula, then maybe it will be easier to find. Okay. So now for the remainder of the talk, I'm going to first I'm going to tell you about the platic algebra. So this is sort of where this general approach of non-commutative Schur functions originated in the work of Lascaux and Schutz and Berger on the platic algebra. And then after that, I'm going to sort of give you the general outline of how this theory goes. And then I'm going to give 3 applications. All right, so we'll let you be the free non-commutative algebra in generators U1, U2, and so on. Okay. And we'll sometimes write just A in place of U sub A. So there's a basis for this algebra. U as a basis of words. Okay, just words in the positive integers. These form a basis for this algebra. Multiplication is just concatenation of words. Okay. All right. So we're going to be interested in certain quotients of this algebra. So the platic algebra is one such quotient. So the platic algebra is the quotient of U by the Knuth equivalence relations which are the following. So for letters A, B, and C, they're the following. Let's say we'll break them into four different relations. Can you guys see this? Okay, so how to think about these relations? So we just want to think that we can swap 2 letters A and C in the presence of a third letter whose value lies in between the 2. So a good way to understand this algebra, or actually any quotient of U by binomial relations, is in terms of
A, B, C are what?
They're just integers, so positive integers. So I'm just using this. This is really U sub A, U sub C, U sub B.
Are you going to tell us a little where this comes from?
Why was not planning to.
This is a reasonable set of relations to impose.
I'm going to tell you in a minute how it's related to the RSK algorithm. Is that will that help you?
Yes.
All right. So the so to understand this algebra, we're going to define a graph that encodes these relations essentially. So the Knuth equivalence graph is the graph. So we have a vertex set. Will just be the set of all words. Maybe later we can take some natural subset of words, but for now let's just say the set of all words. And then we'll say that VW is an edge between two words if V and W differ by a single application of Knuth equivalence relation. So let me just clarify what I mean by this with an example. So let's look at the word 15243, and let's find all its neighbors in this Knuth equivalence graph. Okay. So if I look at the first three letters, what can I do? So these relations say that I can swap 1 and 5 because this 2 is here. It's a sort of lies in between 1 and 5. It's witness to the fact that I can swap them. Okay. So I'll draw an edge there, so I can go to 5, 1, 2, 4, 3. What about the next three letters, 5, 2, 4? Okay, so 4 lies in between 5 and 2, so I can swap the 5 and the 2. Get 1, 2, 5, 4, 3. The last three letters, 2, 4, 3, I can swap the 2 and the 4 because the 3 lies in between. And sometimes it's convenient to put labels on these edges that tell you sort of which three letters you did the swap, the Knuth equivalence at. Okay, so the natural way is to sort of put the position of the middle letter that you used. So this will be labeled 2, 3, and 4. On your handout, has everyone gotten a handout yet? So that first figure is I should take one so I can. Okay, so this first figure is the entire Knuth equivalence graph on permutations of 4. Okay. And the components of this graph are called Knuth equivalence classes. And I just want to remark the relation to the RSK algorithm. So if you don't know what the RSK algorithm is, you can take this as a sort of a partial definition. But so on your handout, you see these components, okay, of your Knuth equivalence graph. And the RSK algorithm, so it takes a word.
So you're always dealing with a finite there's a finite number of U's. That's what I was missing before.
No, it's infinite. I mean, it doesn't hurt. This is just what I've shown you. Just some piece of the Knuth equivalence graph. Right? But yeah, I mean, so it doesn't. We can work with a finite number. It doesn't really matter. Yeah. So it's like the difference between working with symmetric functions in infinitely many variables or finitely many. That's what it will come down to. So we have our RSK algorithm that takes a word W, produces two tableaux of the same shape: the insertion tableau P of W, and the recording tableau Q of W. Okay, and in terms of this graph, what the P of W, it's like two coordinates. So the P of W tells you which component you're in. It naturally labels these components. And the Q of W tells you where you are inside the component. So P of W labels components.
That's the insertion tableau, right?
That's the insertion tableau. Yeah. So this will be insertion, and this will be recording. And the recording tableau, let's say, just tells you where you are in the component, or it's the same as a Knuth equivalence class. Okay, and actually you can rephrase the insertion algorithm as a specific way of walking inside this graph. So you start with some word, you walk by some special set of edges until you get to a special vertex inside that component, namely the row reading word of the insertion tableau. Okay. It's sort of one way to think about the RSK algorithm. So I gave a similar talk to this at UCLA, and Igor Pak asked me, why should I care about the platic algebra if I know about the RSK algorithm? And actually, that's a very good question. So the answer is basically you shouldn't, actually. So the RSK algorithm, if you know the RSK algorithm, it tells you kind of everything you want to know about the platic algebra and more, actually. But somehow that's the point of this approach of non-commutative Schur functions. So what's going to happen is I'm going to sort of tell you how this approach works in some general quotient of U. But
so it will be positivity of what? Positivity of what?
Where is this? You're talking about the title, or?
Yeah. So it will be positivity of what?
It's going to be so one result that comes out is sort of a combinatorial formula for certain Qt Casca polynomials, for instance.
Maybe can you give a little bit more details about the connection to the RSK algorithm? So I wonder, the RSK, you have the word, and then you insert it, and you build up this to fill this Tableau. So, but I would like, this should be a path to this graph. So what is the connection exactly? You would start with the word, and then you would insert. What's the next? Can you give an example? Just one or two?
It's not so easy to say exactly the precise relation, but we can do an example. So let's insert this P of 1, 5, 2, 4, 3. Okay, so this is going to be, I'll start with 1, 5, and then 2 bumps the 5. Yes. And then 4, and then 3 bumps the 5, right? Bumps the 5.
From above. You bump from above into the tableau, or from?
Yeah, I start from the top. Okay. So how did this implement some Knuth equivalence relations? Well, what happens is when you have, let's start with.
You didn't do Q.
What?
You didn't do Q.
I didn't do Q. I'm just talking about P right now. So when you insert a new letter into a Tableau, basically you can realize the insertion into a single row by just doing some sequence of Knuth transformations in sort of 3 consecutive letters. So if I have like 1, 3, 5, and then I insert the 4, then I can realize the bumping of 4 into this 1, 3, 5 with a Knuth transformation at 3, 5, 4, and then at sort of the next 3 letters. And then what I'll end up with is basically a letter. So either this 4 will go on the end of the row, in which case I don't do anything, or it will turn into something where I have a letter followed by an increasing word. And then I do the same thing with that letter to the next row, and so on.
I wonder if I have this Tableau, do I have to think of it as a long word by just concatenating the rows?
Yes, that's how you should think of it in this context. Yeah,
Okay.
yeah.
Okay, then these rules kind of model what you do when you do the RSK algorithm.
That's right.
Roughly.
That's right. Yeah. But it's somehow less information. So
So over there, we should read this as going from right to left, that you start with, in your Tableau, you start with the thing on the right and you want to move it to the left. Is that?
where are you pointing to?
So your Knuth equivalence relations, right?
Yeah.
I want the 5 to be at the end of the row, if it's going to be on that row. So I would want the C, that's like the second one, the C has to get pushed to the end.
Yeah.
So
you can do this with several Knuth transformations. But some, okay, so what the platic algebra is doing is it's only telling you when two things have the same P tableau, and then it sort of forgets the rest of the information. Somehow the point of the approach that I'm going to tell you about is that you can extend this approach to quotients of U where there's no analog of RSK. But there is some analog of the platic algebra. Okay. Okay, so here's the general Fomin-Green theory of non-commutative Schur functions. So let's define, let's say for a word, W of length n, the descent set of W is just the set of indices from 1 up to n minus 1 such that Wi is greater than Wi plus 1. So those two consecutive letters where you go down. Okay. I'll show you an example in a second. All right. The other thing I need is what's called Gessel's fundamental quasi-symmetric function. Okay, so this is denoted Q sub, let's say, so it depends on some descent set, but I'm gonna write it like this. So this is in now commuting variables x1 up to xn, or let's say infinitely many commuting variables. So I have two sets of variables where I'm working with. I'm working with these u's, and I'm also going to be working with commuting xi. Okay. So this is defined as follows. So this is some degree n homogeneous polynomial in, let's say, infinitely many commuting variables, and I missed the important condition. So if I have J belonging to the descent set of W, this implies that I have a strict inequality of the indices here. Okay, so this is not a symmetric function in general, but it's a convenient building block for symmetric functions. Okay. So I mean, if we want to write down a symmetric function, then it's going to take us infinitely many monomials. But with quasi-symmetric functions, I only need finitely many to write down some interesting symmetric functions. All right, we'll see more about sort of why these are useful. But this is kind of a standard tool in symmetric function theory.
You just write down a real small one?
Yeah, I'm going to.
Parsing.
Yeah, so for example, if I take what?
It is a polynomial function. You are primitively monomial.
Let me give an example, then we can ask.
Okay, so say Q sub 1, 2 of x is just equal to E 2 of x, the elementary symmetric function of degree 2. Okay. Because, whoops, sorry, this is, so I've suppressed, let me, this actually depends on n, but I've sort of suppressed it from the left-hand side here. So let me write, let's say, descent set of 3, 2, 1 will be elementary symmetric function of degree 3. Okay. Because this strictness here says that all these have to be distinct. These indices have to be distinct. That's exactly an elementary symmetric function. Okay. If I take, on the other hand, if I take some increasing word here, 1, 2, 3, this gives me my homogeneous symmetric function. Is that more understandable? I'm going to give another example in a second. All right, so we're going to say that the generating function df of some f in my non-commuting algebra U is defined as follows. So let's say, so I'm going to define is df, where D is the map from my non-commuting algebra U to the polynomial ring, which just takes W and sends it to this quasi-symmetric function. So I just extend this map linearly. So I have some words. Okay, I have some sum of words in my algebra U. For each word, I look at its descent set and I build a corresponding quasi-symmetric function, and then I sum them up. That's what this generating function is. So for example, let's take D of the following sum of words in a Knuth equivalence class. Okay, so this is one of the components in your handout. So it's the second to top one. 2, 1, 3, 4, 2, 3, 1, 4, 2, 3, 4, 1. Some Knuth equivalence class. So what does this D do? So I need to compute the descent sets of each of these words, right? So here, 2 is bigger than 1, so there's a descent there, right? But here, 1 to 3, that's increasing. 3 to 4 is increasing. Right? So for this word, I get my quasi-symmetric function of just set 1. Okay. 1 records where that descent is. Plus, what's the next one? So there's no descent from 2 to 3. There's a descent from 3 to 1. No descent at 1 to 4. This gives me q sub 2 of x. And then lastly, no descent from 2 to 3, no descent from 3 to 4, and there's a descent from 4 to 9. So that's the third index, and I get this. So this is a sum of some quasi-symmetric functions whose definition is a little weird, but any guesses as to what this sum is? So I claim that it's actually a symmetric function, and it's one you may know about. So this is the symmetric function, which is the Schur function of shape 3, 1. So these quasi-symmetric functions are convenient building blocks for Schur functions.
So how would you have known it was 3, 1 without going through the whole calculation and then seeing at the end of the day it's 3, 1? Or is there...
We will prove it, well, or not prove it, but it will be a consequence of some theorems that I'm going to write down.
Follow from this representation of the Schur function as a quotient of determinants?
No.
Can you not?
So let's see.
What is Tableau?
If you fire and they develop
What are the sum of the tableau? Tableau.
If you want to think of it in terms of representation theory of the general linear group, you can think of each of these words as representing something in the zero weight space, and it sort of it represents you could say all of the semi-standard Young tableau who standardize to a certain tableau. Actually, it would probably be the recording tableau of each of these. And then when you sum up over all those semi-standard Young tableau, that would give you the character of the whole S31.
Could you write it out what S31 is so that we can check
So do you mean
what it is?
do you mean in terms of semi-standard Young tableau, or?
Because then it's right clear that it's
Then you can
tableau, right?
understand what
So
it
which
is.
tableau?
Okay. Is this what you had in mind? I mean, it's not such an explicit formula.
Here you have three tableaus, which you can write down, and then you can write out one of them. You have three tableaus of the shape.
There are not so many terms. I've written it what it is.
Someone corresponds.
But there are infinitely many semi-standard Young tableau. That's the problem. I mean, so these are infinite. This is an infinite sum. Okay, so but see, it gets grouped. There's a natural way to group these, right? So you can group them as like 1, 1, 1, 2. This would be this would standardize to 1, 2, 3, 4. Okay. Whereas some tableau, like some semi-standard Young tableau, 1, 1, 2, 4, would standardize to 1, 2, 3, 4. Okay. So under this standard, there's only three tableau. There's only three standard Young tableau of this shape. Okay. Each semi-standard Young tableau in infinitely many variables will still also standardize to one of them. And that decomposition of the Schur function is the same as this one into quasi-symmetric function. Is that okay? There was a bunch of other stuff. I mean, but
I don't understand the arrow with the ST. What is
okay, so this, so the standardization map.
okay. I see.
Yeah.
Okay, I know what-
You're okay? Okay, so what you do is you think of like all the ones, you replace them by 1, 2, 3, 4, 5 from left to right. And then all the twos, you replace those by the next letters, increasing.
That would be a third one. That you didn't write.
Yes. Yes, that's right. So 1, and for instance, 1, 2, 2 would standardize to this.
Yes.
You can actually make this completely explicit with a basis and so on. Yeah. Okay, so now I'm going to tell you about non-commutative symmetric functions. So first we'll start with non-commutative elementary symmetric functions. So this is ED of U is defined in the following way. So the sum over UI1 UI2. So basically it's a sum over decreasing words of length D. Okay. So this is some non-commutative version of elementary symmetric function. So we had a choice as to how to define this. We want the goal was to produce some elementary symmetric function so that when we pass to the commutative quotient, then it actually gives us the ordinary elementary symmetric function. So we could really choose any order we like here, but somehow this is the right choice. Okay. So now we can define the non-commutative Schur functions. All right, so we're gonna be working in settings where quotients of U, where these ED, these non-commutative elementary symmetric functions commute with each other. All right, and when they commute with each other, that means that they generate an algebra that's isomorphic to the ordinary ring of symmetric functions. So that's just a polynomial ring in the EI.
So what will they not commute with? If they commute with each other, what are they not allowed to commute with?
Well, I mean, for instance, they will not commute with like U1.
So if you multiply U1, but if you multiply U1 by that, I mean, if you want to stay in the ring of symmetric functions, or you're going to allow yourself to leave that?
I mean, we're not in ring of symmetric functions at all, because this lives in this non-commutative world.
Are you claiming that they commute with each other, EDU, EFU, whatever they commute?
No, but we will state a theorem that starts with that assumption. But I'm just sort of prefacing this definition. So basically, we're going to define these non-commutative Schur functions using the Jacobi-Trudy formula. Okay. In fact, if you like, maybe I can write down the theorem before I write down the definition of J. That will help, but. So here's the theorem. Which says that if the ED U commute in some quotient of U, then the generating function of some F is given by the following. So this is over partitions lambda. This is provided for any F in I perp. So what is this saying? So I take some F. So this I perp is subset of U. I take some F in the orthogonal complement of I under the inner product in which the words form an orthonormal basis. Okay, so I'm making some special choice of inner product here, which is actually important. All right, and I choose this F in this orthogonal complement. Then the generating function of F, as in this definition up here, which we got. So here was one of the examples. And this generating function is, well, it's actually symmetric, and its Schur expansion is given by taking inner products of F with this certain non-commutative Schur function that I'm about to define. Okay. It's a weird thing to see at first, but actually this is not a very deep result. Okay, so this is kind of just translating some language. It follows from facts about ordinary commuting, ordinary symmetric functions in commuting variables.
So I is the idea such that ED will commute modulo I. So
I is some
idea generated by commutators of the functions ED.
No, it's any. Sorry. For some two-sided ideal I.
But there is a minimal ideal you can construct just from all our constants.
That's right. You could so.
Why are we keeping I mysterious?
Yeah, you'll see. There's something else that you need to do for this to be useful.
Okay.
That's not true for that in that general sense.
You're going to take a slightly larger I.
Yes, that's right. But actually, that's a very good question. And one of the things that I've worked on with Sergei Fomin is explicitly understanding that I. And we do, actually. So let me define these J lambdas for you. So this J lambda of U is going to be the determinant. Okay, so here lambda is a partition of lambda prime I plus J. What else? So E. Okay, so this is some determinant of some non-commutative things. So let me write out.
Defining your determinant.
Yeah, I'll write out explicitly how we can define it. So we can define it as just this product. T here is equal to lambda. Okay, so so this is okay, thank you. Okay, so we just chose an order for the product of these E's. Okay. This lambda prime is the conjugate of lambda. But in this theorem, it doesn't matter what order we chose, right?
Does this determinant obey the Kramer's rule? You solve equations?
I'm not
With a non-commutative ring, so we have to order as a determinant each of the monomers by rows or by column.
Yeah, but there's this like red top, Gelfand red top or red top sort of quasi-determinant he calls it is rigged so that Kramer's rule works. I'm just wondering if this is the same.
But
I'm not
so you don't can choose a new one.
Yeah, I mean, in the setting that we're interested in, it doesn't end up mattering. But there actually are some things I've studied here are actually flag versions of this, in which case it does really matter which direction you choose. And there are some, nice properties that determinant still satisfies. I'm not sure if that's one of them.
So in the commutative setting, the first equality is Jacobi-Trudy.
Yes, that's right. Yeah. So this is just Jacobi-Trudy basically. Okay. So this theorem that I just stated, this is kind of just changing some language, but now the theorem I'm about to state is really the deep part and what makes this interesting. So let's see. So in a certain quotient of U by these Fomin-Green relations, so this is in figure 2 of your handout under this Fomin-Green relations. I'm not going to say too much about these relations yet, but I'll just say for now that they're very weak relations. So this implies sort of many things because these are such weak relations. So if this thing that I'm about to write down is true, so J lambda U is the sum over semi-standard Young tableau shape lambda of the column word Okay, so here column word, let me just do an example of some Tableau is just what you get by reading the columns from bottom to top and then left to right. So this is 6, 3, 1, 4, 2, 5. So this is a sum over column reading words of these Tableau in these non-commuting variables. Okay. And the statement is that this holds in this algebra with very weak relations. It does not hold in the most general algebra you can take. That's sort of the answer to your question, now, James. All right. But it holds in this algebra that has weaker relations than the platic algebra. Okay, so it in fact implies that this is true inside the platic algebra. All right. And so now let's see what you can do with this. Okay. Okay, so let me give. So now I'm going to give sort of 3 applications. The first is maybe not quite an application, but is kind of think of as a diagnostic test that everything is working the way it should be. So we're going to let. So we're going to let I equal the defining ideal of the platic algebra, the two-sided ideal corresponding to those relations I wrote down before. Those are on your sheet in Figure 2. And we'll let F be sum of words in some Knuth equivalence class. Okay. So here T is some semi-standard Young Tableau. And note that F, I'm not going to prove this for you, but the sum of the words in a Knuth equivalence class lies in this orthogonal complement of the ideal. Okay. And such sums form a basis actually for this orthogonal complement. The same statement will be true anytime you have the quotient of U by binomial relations.
Does this mean T in semi-standard Young Tableau of mu?
Of shape mu.
Ah, this is mu.
So mu is some partition. This living in this I perp is some kind of unintuitive condition, but it's sort of a natural generalization of a sum of words in an equivalence class. That's how you should think of it. And then this generating function is the sum s lambda x. So I'm just copying from over here this inner product. Okay. And then this non-commutative Schur function is equal to the sum of column reading words. Okay. So I'm using these 2 theorems here to compute this. And now what is this inner product? Well, it looks sort of weird, but if I have on the left is just going to be some sum of words in some set. Okay, so that is the coefficients of all these of all the monomials here are just 0 or 1. And same thing for F. So basically I just have 2 sets and I'm going to intersect them and count the cardinality of that intersection. That's what this inner product is. Okay. So then the question becomes, for this specific case, I have the column reading words of shape lambda, and I want to know how many of them lie in some fixed Knuth equivalence class of corresponding to a tableau of shape mu.
So in this bilinear map, so distinct non-commutative monomials are orthogonal? Or what is this?
Yes, the inner product is where...
It's just that.
Yeah, just monomials are an orthonormal basis. Right. So that's why this inner product is just the size of the intersection of these 2 sets. Okay. And so this is just This is just S mu of x, okay, because there's exactly one column reading word inside each Knuth equivalence class. We know that from the RSK algorithm, for instance. And so it has to be of shape mu for this to be 1. Otherwise, there's no intersection. Okay, and this recovers sort of result of Gessel. In some sense, this equality, that this sum of quasi-symmetric functions over a Knuth equivalence class is equal to the Schur function. This is kind of one of the reasons that these quasi-symmetric functions were defined. Okay. So well, if we believe these theorems, this proves this example that we had before. The sum of quasi-symmetric functions is a Schur function. So we think of these Knuth equivalence classes as sort of maybe our kind of basic building blocks for building Schur functions. So the next example, next application, yeah?
Well, actually out of time.
Out of time, okay. Okay. All right, so if you look at figure 3, then this is another kind of equivalence class for an algebra called the Nil-Coxeter algebra. Okay, so the Nil-Coxeter relations, these are on the front side of the sheet. It's basically like the relations for the symmetric group, except instead of saying SI squared equals 1, you say SI squared equals 0. Okay. And these equivalence classes, the corresponding symmetric functions you get here are what are called Stanley symmetric functions, or stable Schubert polynomials. Okay, so in 1987, Stanley made a conjecture that these things were Schur positive. And then I think several years later, Edelman and Green proved this using something called Coxeter-Knuth insertion. Okay, so this took a significant amount of work developing this different kind of insertion algorithm. But with this framework, you kind of get it for free, actually. I mean, this is the hard theorem, actually, so it's not for free. But you have to prove this, and then the rest of it comes for free. And it basically says you look at this equivalence class in the Nil-Coxeter algebra, and you read off the words that are column reading words. And that tells you the Schur expansion of this Stanley symmetric function. So I'll end there. Thank you.
Questions, comments?
So are you able to obtain some new results using these techniques?
Yeah, that's
Green theorem?
That's the third application I was going to tell you about. So there's a result for what are called 3-column Macdonald polynomials that comes out of this. There's a QT version of Koska coefficients that has been pretty intensively studied since around 1990. And so this gives sort of one case beyond what was known.
So this positivity referred to, well, you explained about the positivity as also about the title of your talk. So that were shown using this theorem. So positivity of what exactly? So which?
So positivity of the Schur expansions of these things, of the DF. So of these generating functions that arise from these graphs.
Expansion in the basis of Schur.
In the basis of Schur functions.
But this means these inner products are all positive or
So okay, so which something I didn't really get time to explain is the key to making this approach work is that you have to write this non-commutative Schur function as a positive sum of monomials in your algebra, which was done in this case by Fomin and Green, but in other cases it's hard or not true, and that's the
products would be 0 or positive.
Or positive, yeah.
Always.
Well, I mean always one. So essentially the approach reduces everything to this showing that this J lambda is some non-negative sum of monomials. So some computation in this non-commutative algebra, which is a hard computation, but it somehow organizes the work for you.
No more questions?
Thank you, James. Then we meet tomorrow again.